Hey guys, hopefully everything's going well. Had a few questions on the homework from Vector. Sorry getting this out late to you guys, but it is what it is. Y'all forgive me. Hopefully we'll see each other sooner or later. But let's just get started with this and we'll go from there. So we had a question on number 4 on the Vector's packet, and it was for part D here. So we were asked to find what is the largest angle of ABC. So the best thing to do here was to actually create points A, B, and C respectively. A here, B here, and C. And if we actually looked at it, if we remember that I is the vector 1, 0, and J is the vector 0, 1, right? It kind of gives us to be able to do A, B, and C in terms of coordinates. Like A here is 4, -1. B is 1, 3. And C is -5, 2. So we can, on a coordinate plane, and you'll have to forgive my drawings, it's not the best, is that we can actually draw these out 5. In their respective positions. So A being at 4, -1, there's A. B being at 1, 3, there's B. And then C being at -5, 2, there's C. And if we actually drew the vectors the way they say in parts A, B, and C, this is what they would look like. But then part D asks us, well, what would be the biggest angle in the triangle ABC? So basically, guys, what we're going to do is we're going to connect A, B, and C as one giant triangle. And if you look at it that way, it's pretty obvious that the biggest angle here is going to be angle B, between BA and BC. So we're going to look for the angle between, and sorry for the writing again, got to forgive me on this one, between BA and BC. So we actually need to find the vector BA and BC respectively first. So let's look at BA. So if we look at BA, B goes from 1, 3 to 4, -1. So BA, what's happening is my x values are going up 3 and my y values are going down 4. And then BC, that vector from B to C, my x values are going down 6 and my y values are going down 1. So those are my respective vectors from BA and BC. All right, excuse me. And so from there, we can now find this angle. And if you remember, we're going to use the law of cosine. So using the law of cosines, we're going to say the cosine of theta equals the dot product between my two vectors. So the dot product between 3, 4, dot, -6, -1, over the magnitude of each one. So if we do the magnitude of BA is basically the square root of 3 squared plus -4 squared, which is 25, or 5, if we want to put it that way. I'm just going to put square root of 25 for this case. And then we can do the same thing for BC. The magnitude of BC would be -6 squared plus 1 squared, which would be the square root of 37. And so by doing this, what we end up getting is that we can do the dot product, which is 3 times -6, which is -18, plus -4 times, so -18 plus 4 over 5 times the square root of 37, which is -14 over 5 root 37. So now we just got to solve for cosine. So cosine theta equals that. So theta is equal to, now remember, we're going to do the inverse. So I'm going to do not theta, but alpha here. And so, all right, guys, sorry about that. Had to pause for a second. So we're going to do alpha here. And so we're going to do inverse cosine of negative 14 over the 5 root 37, which is going to end up giving us, if we use our calculator, 62.59. But since we know this is going to be an obtuse angle, right, my theta is actually going to be 180 that's a terrible 180. Again, touchscreen does not like me. 180 degrees minus the 62.59, which ends up being 117.41. I hope that helps explain what to do on this one, because basically you just create a triangle out of the original. I didn't do A, B, and C because the question was not asked about that part. It's just D. The next question that was asked was, why is the wind out of 45? So I actually did not take out the answer key here, and why. Basically, if you look here, why is W the angle 45? And the reason it's 45 is because it says out of the southwest. So if you think about it, southwest is in this direction, yes? If we were going southwest, but since it's telling us the wind is out of the southwest, it means it's actually going in the other direction. So if you think about it, instead of going there, we're now going in that direction. And remember, if southwest would have been the 225 going that way. However, if we think of the angle that it makes, this is 45, which means over here, that's 45. So if we're coming out of the southwest, that angle that's created here is the 45 degrees, and that's why it's 45, not the 225, because it's not actually pushing us down and left. It's actually pushing us up to right. So it's actually going towards the northeast when it's saying. So it's just a trick of the word there. When it says out, it means it's coming from that direction. So like out of the west, if you ever hear that on the, sorry about that. If you ever hear that on the news or weather, it means it's blowing from the west, which means it's blowing eastward. All right. All right. The next one is one of the car problems, and this one is a popular one to be asked about. So asked us to find two things. One is to find the force to keep the car, and I got the answer there. Find the force to keep the car from rolling down the hill. And the other one is find the component force perpendicular to the street. All right, so this one does take, these are the tricky ones in terms of you have to kind of redraw your triangles. So if we look at part A here, right, we need to find the force that is keeping the car going in that direction, right? We want to find that vector magnitude right there. And so what I'm going to do is I'm just going to kind of redraw this, right? Get these my two horizontals, and we know this angle is 16, and then I'm going to draw my car. And again, it's just a really bad car, but we'll go with that. And what we're going to do is say this car weighs 3,000 pounds. So if this car was on flat ground, that 3,000 pounds would be going right there. It goes in that direction. All right. But we need that vector. So what we're going to do here is we're going to actually redraw this triangle. All right. We're going to draw the vector we need, which is this part. That's our new vector. And it has a force upon it. So I'm going to write F1. And then we know from there, we have a force of 3,000 pounds going straight down. All right. 3,000 pounds going straight down. And so what's going to happen is that we can create a triangle using another one, and this being perpendicular to our first force. All right. Because now this helps us create a right triangle, which we can now solve. Now, we know the angle that was between these two is 16 over here, right? Looking at this, just so we can visualize it. This right here, guys, is a right triangle. So that triangle, we know right here is 16 degrees. We know this is a right angle, which means this angle here has got to be 74, which means that this angle right there, acting between the two, as we see here and here, has got to be 74 as well. So now we can actually solve for that force using trig. So here we go. Since I got the angle and I'm given the adjacent side and the hypotenuse now of this triangle, I'm going to use cosine. So I'm going to say cosine of 74 equals my force over 3,000. So now I just got to solve for the force. So force of F1 equals 3,000 times the cosine of 74. And that ends up being 826.91. So there's part A. And then for part B, it wants to know what would be the component form of the force. Find the component of the force component. So it's looking for the magnitude going this direction from the ground. So basically, guys, we're looking for this other side right here of the triangle we just created. So since we use cosine for the first one, I'm going to use sine for this one and just say sine of 74 equals my component of F2, my magnitude of F2 over 3,000. And again, I'm sorry for the writing. Again, this touchscreen does not necessarily like me all the time. So we see that F2 is equal to 3,000 times the sine of 74, which basically gives us 2883.79. And that's kind of how you have to do it. It's basically recreating a right triangle based on new vectors you're kind of creating with the diagram. So, I mean, if you think about it, this up here now creates this, and this one there creates that, and we just draw in a new one, which is perpendicular to both of those. Oops, sorry about that. I messed up. That one actually, sorry. This here created that one there, and then this one, when we draw it in, creates that. I know that's a lot of squiggly lines, but that's basically what's happening. I'm going to erase some of these just so because they get confusing. All right. If you have any more questions, again, please ask or email me again. And then the last one was number 69 on the review. And it said, write the unit vector in the direction of W. So if you remember, unit vector in just general terms was taking a vector, right, whatever vector we had, and rewriting it over its magnitude. Well, magnitude is basically the square root of its components. Now, in all reality, this is a two-dimensional thing. It has an x and a y, but the z is 0. So this is really almost like doing the unit vector in direction of W if W is just 3, 4. So we can find this with W. It's basically the square root of 3 squared plus 4 squared, which is basically 5, which we know that's the square root of 25, it's 5. So in our case here, W, 3, 4, and 0 over 5 ends up being 3/5, comma, 4/5, comma, 0. Now, I know that's kind of simplistic about it, but in general terms, that's what you're doing. If we had that third component, you'd have to actually do a little bit more calculations with the square rooting and all that stuff to find it. But the principle is still the same. You're still doing this part to find unit vector with your thing. You just have to find the magnitude and then divide the component form by that magnitude for each part, and you would get it. Hopefully it's in the future, guys, and it's going to be a while before we see each other. I'm going to try to do something on live. We'll just check in on you guys, but hopefully everything's going well. God bless you guys.